Hello, this is Hassan Dabaja. I'm from the Laboratoire d'Informatique et des Systèmes at Aix-Marseille University. I'm going to present to you my paper, Data-Driven Crack Detection in the Realm of Structural Health Monitoring, an overview. This paper was presented at the 11th International Conference on Control, Decision and Information Technologies, CODIT 2025. The outline of the presentation is as follows: Introduction, Industrial Application, Signal Processing, Machine Learning, Deep Learning, Transfer Learning, and Conclusion. Let's start with the introduction. Ensuring life safety and reducing inspection costs is a priority for engineers and researchers. Structural health monitoring detects issues to increase structural durability and enhance safety. Structural health monitoring systems encompass components such as sensors, data acquisition devices, transmission systems, databases, analysis tools, and condition assessment methods. An array of sensors such as accelerometers or strain sensors is employed to detect and assess structural issues such as fatigue cracks. Structural health monitoring techniques are categorized into local, which are limited to the area under the sensor's surveillance, and global, that can detect damage anywhere in the structure through a network of sensors. To handle large amounts of sensor data, data-driven methods are replacing traditional physics-based methods. Signal processing techniques are used to isolate critical information. Machine learning algorithms play a critical role in tasks such as damage detection. Deep learning is increasingly applied in structural health monitoring due to advances in big data, cloud-based computation, computer hardware, software, and data science. Transfer learning facilitates the efficiency of training of neural networks, saving time and resources. Big data techniques contribute to the storage, analysis, and management of extensive datasets in structural health monitoring applications. A typical approach in data-driven crack detection for structural health monitoring is as follows: gathering sensor data relevant to the system under surveillance, processing to refine data quality. Signal processing techniques are used to extract relevant features. Dimensionality reduction address feature space complexity. Machine learning models are used to predict damage indicators or health states. These models enable decision making for automated crack detection. These frameworks facilitate proactive maintenance strategies. Let's just start with industrial applications of crack detection. In the civil industry, crack detection ensures the integrity of critical infrastructures. Materials such as concrete, steel, and asphalt are used in civil infrastructure. Cracks can develop in these materials over time, and cracks can extend, resulting in potential structural failure. Examples include bridges, buildings, and dams. In the aerospace industry, crack detection is crucial to prevent catastrophic failures. Aircraft components such as wings, fuselage, and engine parts are subjected to stress, making them vulnerable to cracks that must be detected. Finally, in the maritime industry, crack detection within hull structures prevent catastrophic incidents. Now we will move to signal processing. First, data cleaning and filtering. Data cleaning deals with challenges like noise, outliers, and missing values. Signal processing helps in eliminating noise, filtering signals, and normalizing data. Filtering techniques can be utilized on sensor data to mitigate noise and extract valuable information. Dimensionality reduction. Principal component analysis efficiently reduces data dimensionality by identifying essential components. Moving principal component analysis is well suited for continuous monitoring, offering enhanced accuracy and computational efficiency. Probabilistic principal component analysis tackles the shortcoming of PCA, particularly in managing missing data. Feature extraction. It is to isolate critical features. These features give a profound insights into the significant structural health characteristics. Types of features include frequency domain, time frequency domain, statistical, and mechanical. Temporal analysis of structural health monitoring data. Autoregressive model models is useful to derive reliable damage sensitive features in the time domain. The difference between the model's output and actual data can indicate damage. An example is Zhang Li et Ku propose a data-driven approach utilizing autoregressive models for diagnosing nonlinear damage in civil engineering structures, such as cracks. Now we will move to spectral analysis of structural health monitoring data. The Fourier transform analyzes sensor data to examine frequency components, revealing spectral patterns that indicate structural issues such as cracks. Example, Louis et al. Utilizes fast Fourier transform for low-level feature extraction followed by CNNs to learn local features for crack detection. Wavelet transform is used to extract transient features from sensor data, enabling time frequency analysis and assisting in identifying cracks from signals like acoustic emissions. The utilization of wavelet transform is widely used for vibration-based crack detection. An example is Zhu et al. Introduced a novel wavelet-based damage index for accurately locating and estimating the depth of cracks in functionally graded material beams. Now we will talk about machine learning. Machine learning algorithms allows continuous real-time monitoring and early fault detection. They are used with vibrations and vision information. Machine learning models should be adaptable over time and adjusted to changing circumstances by being retained with fresh data as cracks emerge or structures deteriorate. Human experts play a critical role in validating findings, providing domain expertise, and making important decisions based on output of machine learning models. Unsupervised learning methods focus on structural damage detection by training statistical models solely on data from intact structures. They are more practical than supervised learning methods for implementing early warning damage detection systems in civil structures. Unsupervised learning methods are applied in structural health monitoring for damage detection, system identification, load effect analysis, and load pattern recognition. On the other hand, supervised learning is typically more accurate than unsupervised learning in both localizing and quantifying damage. Supervised learning algorithms effectively tackle both classification and regression tasks in the domain of crack detection. Regression models can estimate attributes such as the size, depth, or location of cracks. Classification models can determine the presence or absence of. Let's move to deep learning. Deep learning models excel in different tasks such as crack classification, crack object detection, and crack segmentation. Supervised deep learning models are widely used for crack classification, while unsupervised deep learning models are used in crack segmentation. Convolutional neural networks are powerful in detecting surface or structural cracks in images, especially when enhanced by contour analysis, edge detection, and color thresholding techniques. Models such as VGG, ResNet, and DenseNet are recommended for crack classification. For handling sequential data from sensors, recurrent neural networks are proficient in capturing temporal dependencies. RCNNs and STMs are well suited for tasks that combine spatial and temporal data. Crack object detection involves fast RCNN, RetinaNet, YOLO, and SSD. Faster RCNN is very accurate in locating and categorizing cracks. Crack segmentation uses models like Mask, RCNN, UNet, SegNet, PSPNet, and Pix2Pix. Transfer learning is essential in structural health monitoring for rapid training of neural networks in image classification tasks. Transfer learning involves utilizing a pre-trained neural network on a large dataset and fine-tuning it for a new analogous classification tasks with a smaller dataset. This model significantly reduces training time by transferring pre-existing weights from the base model. The depth of neural networks poses a challenge demanding substantial time and data for training. Transfer learning addresses this by incorporating prior knowledge, enabling efficient fine tuning with lower computational costs and less expensive data requirements. Various transfer learning strategies are implemented based on the degree of similarity between target and source domains. In the context of CNNs, a common practice involves freezing convolutional layers while fine-tuning full connected layers, optimizing the model for the specific structural health monitoring task. Many pre-trained deep neural networks are frequently utilized in structural health monitoring and crack detection, including AlexNet, VG16, Inception, ResNet, GoogleNet, and ZFNet. CrackNet is a CNN designed explicitly for crack detection on 3D asphalt surfaces. The model is characterized by robustness, performance, speed, and precision and recall rates. Conclusion: crack detection is essential in several domains to maintain structural integrity. Signal processing is used in feature extraction and data analysis, while machine learning models, including deep learning, are highly used for crack detection. Transfer learning is valuable to accelerate and optimize the training of deep learning models, enhancing their effectiveness in crack detection. Challenges in data-driven techniques include real-world applicability, noise robustness, and generalizability across materials. Future research may focus on edge computing solutions for real-time deployment and hybrid models that combine physics-based and data-driven approaches. Standardized benchmarks and synthetic data generation could improve scalability and performance validation. Thank you for your attention.